When we start talking about acid-base reactions, there are a handful of definitions that have came out of the scientific community to define an acid and to define a base. The one that we're going to use today is going to be the Bronsted-Lowry definition, where an acid is going to be anything that donates a proton or considered a proton donor, where then the base will be defined as a substance that is going to be a proton acceptor. Now, we have to think about, well, what is a proton? And so the proton are going to be our hydrogen ions. So we're just going to think about H+. H+ is going to be considered our proton for our acid-base reactions, right? So when we think about things that are acids, we have to think, all right, well, what is going to be a substance that has a hydrogen that will become an ion that'll then be able to be accepted by something else? Now, a really common acid is going to be HCl, hydrochloric acid. When we think about it, it breaks apart into H+ and our Cl ions. Something that HCl reacts pretty easily with is going to be sodium hydroxide. So let's take a look at what the reaction between hydrochloric acid and sodium hydroxide would be. So then, thinking about these definitions again, we have to think the acid is going to donate a proton, and then the base is going to accept that proton. In an acid-base reaction, you really get two products. You usually get a salt, and typically you get water. Not all the time, but for the purpose of this example, that's how we can break it up. So we know a salt is composed of a metal and a nonmetal, and when we take a look at our acid and base here, we can identify each of those. So we have our metal right here, which is going to be our sodium ion, and then we have our nonmetal, which is going to be our chloride ion. So those are going to combine in a 1-to-1 ratio, and then we'll make our salt of sodium chloride. So we have to think, all right, well, what's left? And we have our proton from the HCl, and then we also have the OH, our hydroxide ion. And those are going to combine pretty easily, and then they're going to make water as a result. When we talk about our acid-base reactions, again, this is the Bronsted-Lowry definition, where you have the donation and the acceptance of a proton. And so that is how we're going to look at it for our next couple of examples. For our next example, let's take a look at something a little bit different from HCl and NaOH. Let's say for our acid, we're going to have HBr. And then let's say that our HBr is going to react with LiOH. So we have hydrobromic acid, and then we have lithium hydroxide. Take a second and see if you can predict the two products that we're going to get from this acid-base reaction. So remembering what we talked about before, where our acid is going to be our hydrogen donor, and then our base is going to be the hydrogen acceptor. So they both have hydrogen, but whenever we see the presence of that hydroxide group, that is going to be really good at accepting hydrogen atoms or accepting protons. And so just because of that property, we can assume that the LiOH is going to be our base, and then because of the presence of just that hydrogen or the proton for the HBr, that is going to be our acid. And so when these react together, right, it's just like a double replacement reaction. Well, they'll swap partners. So we got our salt. So we get our lithium bromide. And then we're going to get water again, where it's just H2O. So we can take a look at this for a lot of examples. So let's say now that we have HF, and then it is going to be reacting with KOH. take another second, see if you can predict our products for this next example. And so we're going to have the formation of our salt, right? The metal and our nonmetal. And then we're also going to have the formation of water. Whenever you see the presence of that hydroxide group and then some nonmetal bonded with just one hydrogen, that is a good indicator that you're going to get some type of salt and water, both as products. We're not always going to have the formation of a salt and water in an acid-base reaction because we don't always have ionic compounds acting as bases. So a really common base is going to be NH3, is going to be ammonia. So let's say that we have ammonia reacting with something like acetic acid. Now, it looks like an acetic acid that we have the hydroxide group, and so we want to assume that it's going to be a base. That is not going to be the case here. That hydrogen that comes off of acetic acid is an acidic proton. And then so we can think about acetic acid, in this case, as being the acid, and then NH3 as being a base. If you can memorize that NH3 is going to be a base, then whenever it is in the presence of something else, it's a good indicator that that other substance is going to act as the acid. And then so let's think, what products are we going to get from this? So take a guess. Remember that definition of proton donor and proton acceptor, and see what you can come up with. So once that acetic acid gives away its proton, we're actually just going to be left with an ion, with a charge. And so if we're net neutral in the beginning, we're most likely going to be net neutral at the end as well. So your acid is going to then become negatively charged after it gives away its proton. And then once our base accepts that proton, gains another hydrogen, it's going to be positive. And so now we can't really refer to these as being a salt and water anymore. So this is when we're going to start to come up with these terms called conjugate pairs. So let's try to pair these up. Thinking about our base first. What did our base become? Once the base acted as it typically does, and it gains a hydrogen, it became the NH4+, the ammonium ion. And then so that is a pair right there. And then we want to think, okay, well, what about our acid? What did the acid become? Once it lost its hydrogen, it turned into our anion here. And then so that is our second pair. And then so these can be considered our conjugate pairs. So the purpose of talking about these conjugate pairs is that once we get into a system that can reach equilibrium, we can think about the conjugate pairs or the conjugate substances in the reverse direction. So then if we're now looking at our products becoming the reactants again, what would the NH4 act as? What would the NH4 do with its hydrogens? Is it going to give those hydrogens away, or is it going to gain additional hydrogens? Because it has that positive charge, it is going to act as the acid. It is going to give them away. And then so even though NH3 was originally a base, the NH4 would be considered the conjugate acid. And then we can think about the same idea for our CH3COO ion. If we're looking in the reverse direction, what is it going to do in terms of a proton acceptance or donation? With a negative charge, it is going to readily accept protons. And so in the reverse direction, we can think of it as acting like a base and so it would be considered the conjugate base. So when we start to think about our conjugate pairs, the acid turns into a conjugate base, and then our base turns into a conjugate acid. So again, if we do not have a salt and water as products, we are going to start thinking about these conjugate pairs, the conjugate acid and the conjugate base, to start to describe the properties of these products and whether or not they're going to act as an acid or a base in the reverse direction of our reaction. So for this example, we have H2SO4 reacting with water. And so we want to think about that Bronsted-Lowry definition still. What is going to act as the proton acceptor and what's going to act as the proton donor? Water has this unique ability to act as an acid or a base, depending on what you're mixing with it. So whenever you see water as a reactant, you want to think, what else is there? So we have H2SO4. H2SO4 is going to be considered an acid. And since it is going to be readily available to donate a hydrogen, in this instance, water is going to act as a base. And so try to predict our products, right? If we can assume that the H2SO4 is going to lose a hydrogen, what will it become? And then what will happen to water once it gains a hydrogen? We will have the formation of our hydronium ion. Once water accepts another proton, it'll become H3O+. And then once our H2SO4 loses a proton, it also becomes an ion with a negative charge. So now try to come up with your conjugate pairs. So our acid turns into something, and then the base turns into something. And so how would you assign the conjugate pairs for these species? So since water accepted the hydrogen, its pair is going to be the H3O+, our hydronium ion. The H2SO4 lost a proton, and afterwards it became the HSO4 anion. And so those are going to be our conjugate pairs. Now we want to think, well, what is the hydronium ion going to do in the reverse direction of this reaction? Since it has that positive charge, it will become the conjugate acid. And then our HSO4 minus is going to become our conjugate base. So again, you want to think about it in the reverse direction. Is it going to lose or gain a proton? The positive charge will be indicative of an acidic property, and then the negative charge will be indicative of a basic property. So we can assume just based on the charges that they have, how they will act in the reverse direction. For this last example, let's reuse NH3. And let's say that NH3 is going to react with water. We know NH3 has the tendency to act as a base. So we can assign a basic property to NH3, right? For the purpose of this, we'll just call it a base. Remember, I said before that water has this unique ability to act as an acid or a base, depending on what you're mixing with it. And so in this example, we know that NH3 is going to be a base. And so that's going to force water to act as an acid. So then what are our products going to be for this last example? So since NH3 is going to act as a base, we know it's going to gain protons. When it gains that proton, it's going to have a positive charge. So we have our ammonium ion. Once water donates one of the protons to NH3, the acid, after it's done reacting, is going to have a negative charge, and so that gives us our hydroxide ion. And so for this last bit, let's try to make up our conjugate pairs and assign the conjugate names for our NH4 plus and our OH minus. So our NH3 turned into our NH4, and then our H2O turned into our OH minus. So in the reverse direction, we want to think positive charge acts as an acid, so it'll be considered the conjugate acid. And then in the reverse direction, the negative charge is going to act as a base, and so our hydroxide ion is going to be considered the conjugate base.